Multi-view approach for drone light show. The Visual Computer, 2023. Original article by Kai-Shun Wang, Shu-Ting Lin, Sheng-Shi Hu, Ru Tai-Song, Main-Te Shi. Abstract. Drones, or precisely quadrotors, have been increasingly used in the field of robotics and is also in entertainment. Coordinated multiple drones that form visual presentations through their equipped LEDs are known as drone light shows, YBL-M, KISS, and so on. Drone shows creative potential and best practices. Such a performance offers visual enjoyment for a large audience, particularly in festivals. However, the majority of current drone light shows are manually coordinated by personnel using software. Drone light shows also have limited viewing range, thereby preventing the audience from getting a good view of the actual performance. This study proposes a method to provide multiple visual presentations in accordance with multiple viewing angles. We use visual hold to filter out the candidate areas that form input images and takes projection error and classification values as weight for optimization. Consequently, the proposed method reduces the number of drones needed to form a multi-view structure for visual presentations. Furthermore, to meet the demands of performing the animation in multi-view structure, we implement the FLY algorithm to locate the most suitable corresponding points between two different structures, and then generate the shortest fly paths without collision. Experiments conducted in our simulator provide additional insights and discussions, and each factor is visualized to provide an improved understanding of our approach for multi-view drone light shows. Keywords: 3D Ambiground, drone light show, integer programming. Introduction. The drone market was expanded rapidly in recent years with the maturity of drone technology and introduction of the relevant regulations. The use of drones, which originated from military and surveillance use, has extended the entertainment sector, other than pure shooting and filmmaking. Well-known drone manufacturers such as Intel now provide drone light shows as a service for large-scale outdoor festival events. Remarkable performance can be achieved by controlling a swarm of drones and well-designed light transitions. Hence, a new form of entertainment has opened new business opportunities. Compared with fireworks shows, drone light shows offer more environmental protection with less air pollution, less noisy, and they are safer because no explosions occur. Moreover, modifying and designing complex graphics are considerably easy, thereby providing substantial budget savings. However, just as fireworks shows have limited best viewing areas, drone light shows also have such a constraint. If the audience is not within the expected viewing area, then a pleasant viewing experience will be difficult to achieve. Furthermore, the more complex the composed visual presentation, the more important the viewing position. To provide superior experience, the audience are often congested in the required viewing range. Other alternatives to have the same experience is to include rotating the entire drone group from the audience. However, alternatives can be time consuming and minimally efficient because a standard quadrotor's battery can only support a flight time of 15 to 20 minutes. This study proposes a method that allows the audience to view different visual presentations from different angles without substantially increasing the number of drones. First, we construct a multi-angle viewable structure with the given images. Second, we calculate the flight path that provides collision avoidance, thereby enabling the swarms of drones to safely transit between different structures. 2. Related work. 2.1 Three-dimensional ambigram. A multi-angle viewable structure of multi-view structure provides different visual presentations from varying perspectives. This structure is known as three-dimensional 3D ambigram in the field of computer graphics and arts. The practice of generating 3D objects from two-dimensional 2D images can be traced back to 3D objects reconstruction. In particular, 3D objects reconstruction is the process of simulating human guessing actual objects based on what they see. Through observation from different angles of view, structures of large objects can be inferred. Different objects, angles of views, and the amount of input data can vary differently. Hence, the related research has often focused on optimization methods to improve the accuracy of object reconstruction. One of the commonly used techniques in 3D reconstruction in the visual whole concept, assuming that the foreground and background pixels of the images can be separated. Several generalized cones are back project to the images based on observation positions. The intersection area of several generalized cones in the visual whole will represent the geometry of the objects inferred from the outlines of the given images. The visual whole concept is also applied in shadow arts. Shadow arts is a type of artistic presentation technique in which 3D objects are manually crafted by artists, and different types of presentation can be seen from different directions when viewing the objects. Although visual whole calculation can produce an approximate shape inferred from the outline of given images, images used in traditional visual whole research are projected from exact 3D objects using various perspectives. However, random projected images are prone to contradict each other. Shadow art proposed a method to solve this problem. The visual whole area was calculated to determine the contradictory part, and an image deformation is applied to solve the contradiction. This method enables the algorithm to aid the design of multi-view structures, resulting in shadow art no longer relying on artists' manual creation. Studies on the contradiction of a multi-view structure are explored are explored later using mathematically relevant significance of the consistency between input images and duality under specific geometric conditions. The related research has extended such a representation of arts to other fields based on similar concepts, such as constructing buildings that can be viewed from multiple perspectives, or producing metal wire joints with multifaceted meaning. In a similar method, for example, in shadow art, visual whole is used to get an intersected volume space, finding consistent pixels, and employ as writing as possible shape manipulation to optimize the volume space iteratively. However, in the practical case of drone light show, the number of drones is limited. Instead of directly using solid images like shadow art, we processes solid images first to obtain the target images, and then use the concept of visual whole. That is to say, different from the classic visual whole. The volume space in our method is determined by the field of view of the viewing position. Finally, the target images are used to optimize to select a set of points in the volume that can best represent the input image at each viewing position. According to the proposed method, our method is still fundamentally different from shadow art. Shadow art is to find an optimal volume shape, which is a challenge in the drone light show. Our method is to select a set of optimal points from the volume through integer programming, which will have a better capability to present the feature lines of the images. 2.2 Collision avoidance algorithm. With a multi-view structure, decompose formation of drones and their position are confirmed for unnamed aerial vehicles, UAVs, to perform transformation between structures, a necessary aspect is to ensure that drones will not collide into each other. Unlike UAVs, cooperative obstacle avoidance on the ground is better developed and often applied to movements of multiple robots. Similar problems also use Bernstein-Bezier curves, or shortest path, to optimize the path curve. Given that drone flight shows are often performed in open areas, such as the sky, additional obstacles in this scenario are excluded, and only drones that perform during the show are considered for collision avoidance. Pythagorean homographs is one of the most used techniques. Pythagorean homographs is one of the most used techniques in solving collaborative avoidance for aircraft. Although numerous methods can provide a global optimal solution, space-time complexity will eventually increase in accordance with the number of drones. A global optimal solution is not feasible because actual drones light shows often use hundreds and thousands of drones. Therefore, a local optimal solution by calculating only the position and velocity of drones in neighboring area is proposed to provide velocity of drones in neighboring area a neighboring area is proposed to provide real-time avoidance. This study adopts the local optimal solutions and enhance avoidance with parallel computing and efficiency optimization to enable the smooth transformation of each multi-view structure. 3. Methodology. In our multi-view structure generation method, the input is divided into viewing conditions and group of two or three images. In addition to input images, users can also just adjust the parameters of viewing conditions according to the usage situation, referring to figure 1. Theta E is the included angle between viewing position. R and H represent the radius of the site and the center A of multi-view structure. After the input is completed, the viewing conditions part will use the concept of visual whole to generate volume based on the frustum of viewing position, and the input images will be processed for better results with bounding box alignment, resizing these images to the same size, and performing binarization and simplification to obtain the target images. We can reduce the inconsistent points in the optimized result. Finally, the integer programming method will be used to select drone positions from the volume in the optimization stage. The target images will be used to assist in optimizing the cost function to optimize our multi-view structure, which is select from the volume space. Figure 2 shows a scenario of the proposed drone light show. 3.1 Multi-angle viewable structure. 3.1.1 Set up and image binarization. Given the input images, each image I is appropriately scaled, adjusted, and binarized to separate the image background and obtain its foreground pixels. U, V. 3.1.2 Generating the visual whole. A set of drones candidate positions are constructed on the basis of the visual whole concept. Projector VPI is applied to each drone DJ and its position P, etc. 3.1.3 Optimization Projection Error. In an ideal situation, images projected by the current set of points in each viewing position should correspond to the input images. However, the projected images in the majority of cases may not match the input images. To solve this problem, points that fail to satisfy the input images from all viewing positions are added, and a projection error value is calculated for all points. This idea enables each pixel of the given images to be projected as much as possible. The projection error for the foreground pixels in each image, MI, is set to 0, and each pixel away from the foreground pixels increases the error. The projection error formula is shown in algorithm 1. The priority is to select points with low projection error on each image to optimize the structure. The idea is to select points close to the image contour, while points deviating from the contour are avoided to prevent identification difficulties among the audience. Three point 1.4 Optimization Classification. Although the projection error enables the multi-view structure to have points close to the image contour, it is prone to favoring one image, while allowing other images to have higher error values. Even though the sum of the square projection errors is minimal between candidate points, errors accumulated may still render the projected image unrecognizable. However, if points only satisfy one image, then additionally points will needed to fill in the gap to meet the requirement for all images, thereby increasing the local number of points needed. To solve these problems, a classification value is added to each point to maximize the number of foreground image it cannot project. When both points have the same projection for value, points that satisfy more images will be selected. Points are classified according to the number of projections outside the viewing range of each viewing position. The more the number of points located outside, the larger the value. Hence, points with less value Three point 1.5 Image simplification. To further reduce the number of points needed for a multi-view structure, we consider the contour extraction and contour interval sampling methods. Through the appropriate combination of both methods, we reduce the points needed with retaining recognizable images for all viewing positions. In terms of image simplification, the current method adds projection set for each foreground pixel, which set the number of increases and as images become markedly complex. Consider, for example, of a silhouette in which filling all foreground pixels requires a huge amount of projection sets. Therefore, contour extraction was used to simplify images into contour lines. However, the human eye only requires a rough outline and some features to effectively reorganize images. Hence, drones do not necessarily have to form continuous lines to project recognizable images. Therefore, contour lines are spaced according to the ratio of the image length and sampled as equal intervals as the outer frame of figures. Hence, reduce the number of projection sets that should be satisfied to reduce the required number of points while preserving the image shape characteristic. 3.1.6 Optimization. Range searching. Simplified images provide additional spaces for buffer, and a slight position change between discrete points does not significantly affect the overall contour recognition results. Hence, we increase the range that the projection set can satisfy based on the image length radio to explore superior options around the target pixel. The definition of a projection set is expanded from a collection of points projected to a target pixel to a collection of points projected to an area of pixels around the target pixel. The area is calculated based on image length to satisfy image constraints while providing additional options. If no superior options are available, then the optimization result will remain the same. However, a large searching range should be avoided. Otherwise, several projection sets may be selected from the same pixel, thereby rendering the image unrecognizable. Given that our simplification method has equal distance and uniform sampling, the search range is set to half of the contour interval. Thus, the projection sets should be able to cover the image while avoiding excessive overlap owing to the search range. The search range expansion is presented in Figure 8. Combining range searching and image simplification reduces an optimized structure with less pixels to satisfy while retaining a recognizable outline. 3.2 A multi-view structure transformation. To perform a multi-view drone light show animation, drones need to switch positions between several structures without collision. To transform between structure, a light path is calculated for each drone from two sets of position to generate a pair of origin and destination points. Each pair is determined using the Hungarian algorithm to confirm the position and status of drones in different time series. To avoid collisions, real-time avoidance algorithms are used to calculate the appropriate flight paths between drones at different time series. Figure 10 represents process of multi-view structure transformation. 3.2.1 Transformation between two multi-view structures. To allow changes between structures, the flight process of a drone is treated as a continuous action. Current path planning is treated as a continuous action. Current path planning algorithm often require a pair of origin and destination point for each drone in different time series. Different pair of positions will have different effects on the time and distance required for flight. Hence, choosing a superior pair of points can reduce the occurrence of detours and transposition during movement. However, path planning algorithm cannot be directly applied because the number of points in each structure may not be the same. First, points are adjusted to maximum according to the highest number among structures. Second, additional points are controlled by triggering drones light. Lastly, the closest correspondence for each for each point between adjacent structures. In research, in practice, we regard the origin and destination points as agents and tasks, respectively, in the assignment problem. The distance from the origin point to the destination point is regarded as the cost of the agent to complete the task. Using Hungarian algorithm, two structures with adjacent time series are processed in batches to obtain the smallest cost, thereby resulting in the shortest path composed of pairs of points. For drones that are not assigned to a destination, their lights are turned off and remain idle at their current position. If the next structure requires these drones to move, they can move early to their respective destination points to await further instructions. Hence, the position change, and light status of each drone during the entire show are generated to provide simulation for path planning. 3.2.2 Collision avoidance during structure transformation. On the basis of quadrature movement and efficient consideration, real-time obstacle avoidance (RVO) library and the related concepts are applied to provide collision avoidance. The speed of two objects can cause collision in the next time interval is regarded as a set based on the real-time obstacle. The real obstacle avoidance concept. Thus, collision can be avoided by providing a speed that is out of this set. In practice, transformation duration is divided into maximum size of time intervals, and each drone moving toward its destination at constant speed without collision is treated as a valid move. Thereafter, the position of drones is updated. If a collision occurs, RVO library is used to search for speeds that will not cause a collision. The process iterates until all drones have flown to their respective destinations, thereby reducing a flight path for each drone to transit between structures without collision. To further improve computing speed is calculating a collision-free flight path. A limit search range is provided. Each pair of origin and destination points for structure transformation are connected to output the final animation. 4. Multi-view drone light show simulation and discussion. For simulation, we used Unity to demonstrate our multi-view drone light show, thereby enabling us to observe and evaluate the structure and results of each optimization through two indicators and number of points in the structures. We also compare and observe the influence of different parameters to the results. Lastly, a post-system lighting effect is added to considerably stimulate actual drone performance. 4.1 Environment and tool setting. This research uses Python for algorithm implementation and Unity C for animation and user interface, in which the Unity version is 2019.2. We adopted the mixed integer program solver using CoinCBC in Google OR tools to solve the optimization problem. The implementation environment is window, etc. Figure 12 shows our viewing result based on three different viewing positions to avoid image conflict, because by the viewing position, by being considerably close to each other, we set degrees so many degrees in our experiment to get a better performance. The parameter theta also can be set in different angles to fit user's case. In addition, the field of view f of v angle is set to 30 degrees to markedly observe details in the composed image, and the parameters r and h are both can be tuned by users. In our experiment, parameter r is approximately 1 time the parameter h. Moreover, the audience needs to look up at an elevation angle of 45 degrees to view the drone show. 4.2 Indicators. The optimized structures and the original simplified images are compared to evaluate the quality as illustrated in figure 13. The top row shows the process's result of the input images. Second row shows the optimized result from each viewing position. While the bottom row, we use a threshold to restrict the the point's projection error weight. We set threshold to 32 in bottom row. That is to say, when the point's projection error weight greater than threshold, this point will abandon. After applying threshold, we can get a less noise projected view, but might have less capability to descript image contour. So user can trade off apply how much threshold or not. In addition, mean absolute error MAE and mean projection error MPE are shown in table. Matched points are points overlaid onto the original image pixels, and unmatched points are meant to overlay on the original image pixels but fail. Extra points are additional points to make other projected images be recognizable, but an unmatched pixel is considered in this projected image. MAE is the radio of difference between the optimized structure and original image. MPE is calculated using the optimized structure and simplified image in algorithm 1. The MPE value indicates the overall distance of points deviating from the main contour. 4.3 Experiment result and discussion. The experiment settings indicate that each case of the selected images has a different type and size. Images are processed to produce a corresponding multi-view structure, and the output of image simplification and projected image are shown in figure 14. Because of the limitation of three viewing positions restrictions, it is hard to find a perfect set of points that fit the target image in each viewing position. In our experiments, we provide a figure comparing two viewing positions in Appendix C. Moreover, we also comparing shadow art which is Appendix D. 4.3.1 MAE and MPE. At present, MAE can be used for analyzing the difference in the number of points between the generated structure and original image. However, a high MAE score is not equivalent to an unrecognizable projected image because the human eye has different ways of recognizing images. Hence, MPE is proposed and added to substantially evaluate the outcome of the projected image. That is, the distance of points deviating from the main contour can markedly contribute in measuring the identification of the projected image. 4.3.2 Image style type. Given that we use defined contour function in OpenCV library for contour extraction, different types of image style will have varying degrees of influence. We apply different image style type to C, O, and K and Q. 14 as an example. Figure 15 presents the different image style. Table 2 is statistics of figure 15. In table 2, case 1 shows the optimized results with simplification, while case 2 performs image simplification while filling up a solid area. Cases 3 did not undergo simplification, which only contains outline. The results shows that our simplification method is effective because computation time and the necessary points for structure have been substantially reduced. Optimization weight. Figure 16 shows the result of different weights overlapping the original image. Projection error is an intuitive method, but points with small projection error often cause numerous points gathering around the contour, thereby eventually leading to limit recognizable results. The first row classification focus on prioritizing points that satisfies numerous images. However, using classification alone may enable some points that are evidently distant from the main contour selected, as shown in figure 16, second row, in which the middle image C has points around the contour. By combining projection error and classification in 1.4 radio, experiment results shows that projection error enables points to move close to the contour, while classification prevents sufficient noise around the contour to enable superior recognition. Apart from visual adjustment, mixed weight also further lowers the number of points required for a multi-view structure, which is consistent with the number of drones used in actual performances of drone light show. The yellow and red box show the significant result of points adjustment, thereby leading to significant recognition of projected images. 4.3.4 Image simplification result. Image contour is simplified into dots based on different intervals, and a different search range is applied to evaluate the output performance. Our result indicates that points needed for a multi-view structure is reduced from thousands to hundreds, which is consistent with the number of drones in the performance. Interval sampling reduces the number of points in the main contour, but simultaneously increases the influence of noise. Therefore, a large interval should be avoided because it may cause noise greater than the main contour, which renders difficulty in identifying the image. In our experiment, a sideland radio of 0.3 is selected as a result of the evaluation shown in figure 17. However, we suggest a range between 0 and 0.3 and 0 and 0.5 as the appropriate interval radio for contour sampling based on different image style types image style types and sizes. 4.3.5 Influence and range searching. While increasing the search range by 1 pixel, points with minimal projection errors will fall within the search range of the main contour and may be selected as the final result during optimization. Therefore, increasing the search range can effectively reduce the noise produced. However, if we attempt to widen the range, then there is a chance to find points with small weight and reduce additional noise. This attempt will also render the main outline to deviate, thereby resulting in loss of outline details and rendering the image less recognizable. In addition, we discovered that the more simplified the image, the lower the applicability to expand the search range owing to a lack of detailed outline. If the search range is widened under these circumstances, then the human eye will have difficulty judging which points constitute the same line segment. In our experiment, a researching range of half the interval between points during contour sampling can sufficiently reduce noise while retaining contour details. Therefore, a range of 1 pixel is the most ideal choice. 5. Conclusion and future works. This study proposes a form of drone light show and applies the concept of 3D ambigram to create a drone performance that can be viewed from multiple perspectives. On the basis of experiment settings and inputs, candidate points and weights are calculated for an appropriate projection set through the integer programming optimization model. With a multi-view structure, we also adopt MAE and MPE to evaluate the result. Thereafter, we create pairs of origin and destination points from consecutive multi-view structures to form an animation. Lastly, real-time collision avoidance is applied for path planning to complete the drone light show. A simulation of drone light show using this algorithm is provided for improved demonstration. Therefore, our method increases the viewing area and apply methods. Example, contour extraction, searching range, and optimization weight. Reduce the number of drones used in a multi-view structure while maintaining a recognizable projected image in each direction. We also perform various experiments, evaluations, and discussions on using different types of image style. In the future, we will endeavor to improve the capabilities of our user interface, thereby enabling users to efficiently judge image conflicts caused by the current image combination. Additional optimized information is provided for users, significantly reducing the image cost in conducting experiments on different parameters, thereby providing a rapid and convenient experience. Future work also includes real-world flight experience and physical environment constraints evaluation for generated flight paths that are considerably realistic and close to actual simulation situations.